This is Euclid Book 10, proposition number 79. To an apotome, only one rational straight line can be annexed, which is commensurable with the whole in square only. Let AB be an apotome. This is an apotome right here. And BC an annex to it. Okay, we're going to annex BC to AB. Okay. Therefore, AC and CB are rational straight lines commensurable in square only. AC, CB, they're both of these lines, okay, AC and CB, they're rational straight lines, and the only time they're commensurable is when they're square. This is by Euclid Book 10, proposition number 73. I say that no other rational straight line can be annexed to AB, which is commensurable with the whole in square only. For if possible, let BD be annexed. We're going to add BD to this. Therefore, ADDB, okay, are also rational straight lines commensurable in square only. This is by Euclid Book 10, proposition number 73. Now, since the excess of the squares on ADDB, now where did we get all these squares? Okay, we took line AB and we made a square out of it. All four sides are going to be the length of AB. We took BC and we made a square out of it. And all four sides of this square are going to be the length of BC. We did the same thing to AC. We took the whole length right across here, and we made a square out of it, and all four sides are going to be the length of AC. We did the same thing to AD. All four sides of this square are going to be the length of AD. DB, we took this length right across here, and we made a square out of it, and all four sides of that square are going to be the length of DB. Okay. Now then, what about these rectangles? Well, we took the length of AD, two sides of the rectangle will be the length of AD, and two sides of this rectangle will be the length of DB, which is this one right across here. Same thing here. We have the length of AC, two sides of this rectangle will be the length of AC, and two sides of this rectangle are going to be the length of probably CD. No, it's CB. CB. Okay, so the length of this is going to be the other two sides. Okay. So then, now since the excess of the squares on ADDB, so what we're going to do is we're going to add this area right here and this area right here together. Okay. Now, at this point, we're going to say that there is more area. If you add these two together, there's more area in that sum. Okay, there's more area in the sum of these two than there is in the. Okay, let's slow down here, because this gets real wordy here. The sum of these two areas here is going to be greater than something else. What is it going to be greater to? Well, we're going to take this area right here, we're going to multiply it by 2. So the sum of these two is going to be greater than twice the area of this. Okay? I know that's real tricky here. How much greater is the sum of these two than twice the area of this? Well, we don't know. But we do know that whatever number we get, okay, if we subtracted twice the area of this from the sum of these two, that total, whatever we get left, is going to be exactly the same amount as what? What is it going to be the same amount of? Okay. What we're going to do is we're going to take AC and BC, we're going to add it together, okay? And that sum is going to actually be greater than twice the area of this. Okay? So, if we subtract twice the area of this from this sum, and we subtract twice the area of this from this sum, those two totals will be exactly the same. Because they both exceed by the same, the square on AB. Okay. Both this here and this sum here is going to be bigger than the area of this. This is by Euclid Book 2, proposition number 7. Therefore, alternately, as if we needed more. Okay, so the excess of the squares on ADDB. Okay, so we're going to add these two together. Over the squares on ACCB, which is these here. Obviously, at this point, we're going to be able to say that this sum is greater than this sum. Is the excess of twice the rectangle ADDB over twice the rectangle. So, twice this area is going to be bigger than twice this area. But the squares on ADDB exceed the squares on ACCB by a rational area. Okay. So what that means is that the sum of these two areas is rational. The sum of these two areas is also rational. Therefore, twice this area exceeds twice this area by a rational area, which is impossible, for both are medial. Twice of this area and twice of this area are medial. And this is by Euclid Book 10, proposition number 21. And a medial area does not exceed a medial area by a rational area. This is by Euclid Book 10, proposition number 26. Therefore, no other rational straight line can be annexed to AB, which is commensurable with the whole in square only. Therefore, only one rational straight line can be annexed to the apotome, which is commensurable with the whole in square only. Wow, what a proof. And if you think that was bad, wait till you see the next one. Alright, I will tell you more in a future video, so I want you to stay tuned.